Bam! Mr. True. In this video, we're going to do 3 examples where we start to understand the similarities and the differences between a function value. What do you get from a function at some value of, let's say, x equals c, some value of c, which is going to be an independent value, and a value of a limit at that same point. We're moving into calculus, and you should have had some understanding of limits, or maybe you're in pre-calculus right now, but exposed to limits for the first time in pre-calculus. The reason why it's pre-calculus, and you need this understanding of the difference between a limit and a function value, because limits are the foundation of the entire course of calculus. You really have to have a good understanding of what that really means. Now we're not going to be doing delta epsilon proofs here. We're going to be analyzing the values of limit values using a graphical approach to these problems. There are going to be 3 examples, so it's going to take a bit. We're going to do some review of graphing parabolas, putting this into standard form or vertex form so we can graph it properly, how to reduce rational functions, and identify, get a little reminder from pre-calculus, the difference or how to identify where a rational function is going to have a whole or a vertical asymptote, maybe a little bit of discussion about horizontal asymptotes as well, and graphing piecewise functions. I like doing lessons, not examples. So again, in the description, you got a timestamp to jump ahead to any one of these 3 examples, as well as a link so you can find my other 700 plus math videos I've made over the last 10 years or so. So let's get started. We're going to be taking a look at number 1. Now, you have been messing around with polynomials and specifically quadratics for quite a while now, all the way from Algebra 1 through Algebra 2, Geometry, and Pre-Calculus. But we really do need to know all of those skills. The 99% of calculus is actually algebra. So we're going to analyze, I want to analyze the value somewhere along this parabola, its function and its limit. But first we want to know what it looks like. Maybe a little overkill for this particular example, but let's get a review of graphing parabolas. We have, we're going to go through the process of completing the square to put this into, my book calls it standard form. We're going to look at this value of b and work through the completing the square process. So I'm going to have y is equal to x squared minus 4x. I'm going to move the plus 3 off to the side. And I'm going to go through the little completing the square process to allow me to see where the vertex is of this parabola. And there's another technique. We can find the x of the vertex by doing negative b over 2a, and then plugging that value of x back in here to find the y. But completing the square is a really important technique for a lot of math classes, but calculus as well. So we're going to take half of b. We're going to take half of negative 4. We're going to square that. Half of negative 4 is negative 2. Negative 2 squared is equal to 4, and we're going to add 4 into this equation, and we need to keep this equation balanced. I want to make the right-hand side of this equation here just look different, not actually be different. So for adding 4, we have to subtract 4, and 4 minus 4 is equal to 0. So I've effectively added 0 to the right-hand side of this equation. 0 is the additive identity, so I just made it look different, didn't change its value. When you complete the square, again, if you need as much review as you enter calculus, that's okay, as long as we pick up these skills as we go. And if you don't need it, well, nice job. But we have set up a perfect square trinomial, a quadratic that is very easily factored. The factors of positive 4 that add to negative 4 is the same thing, negative 2 times negative 2. So we have here y is equal to x minus 2 squared, and on the right here we have negative 3 plus 4 minus 3, which is going to come out to be negative 1. So we have an equation of a parabola opening up with a positive leading coefficient. We can see that much here. Maybe we can let x equal 0 and find that y-intercept. But in this format, we can see that the vertex of our parabola is going to be, the x of the vertex, of course, we should know, is going to be 2, and the y-coordinate of the vertex is going to be 1. So our vertex is equal to 2, negative 1. You want to change the sign of that value, if you will. It appears like you're changing the sign as you pull the 2 out. And with that positive leading coefficient, we're looking at a parabola opening up. So we have a vertex whose parabola is at 2, -1, so over 2, down 1. And this parabola has a leading coefficient of 1, or we have an a value, if you will, here in front of the squared parentheses that has a coefficient of 1. So there's no vertical stretch applied to this parabola. So what we can do is we can go from the vertex up 1 over 1 and make a dot, up 1 over 1 and make a dot. And I'm just really kind of interested in a sketch of the parabola. We can talk about solving this and finding x and y intercepts and whatnot. But we're going to have a parabola that looks basically something like this. Messed up the left-hand side there a little bit. The reason why I'm sketching this parabola is I want us to recognize that this parabola is continuous everywhere. I was able to draw the entire parabola without ever having to pick up my piece of chalk. Thus, this parabola is continuous everywhere. Yes, talking about a little bit about definition of continuity as part of this discussion as we enter the idea of evaluating and seeing, is there a difference between a function's value and a limit at that same value of x? So let's talk about, here at 0, 3. What is, as we look at this parabola, and I did not use function notation for this, which now I'm kind of wishing I had, so let's call this f of x equal. What is f of 0? Well, f of 0 is 0 squared minus 4 times 0 plus 3, which is equal to 3. Okay, great. What is the limit as x approaches 0 of x squared minus 4x plus 3? Now, the textbook I teach out of for calculus just jumps right into visually and numerically with t-tables, analyzing the behavior of an equation or a function, and asks you to identify the limit. And then in the next section we start talking about, and in the next section after that we do a lot more discussion about one-sided limits. But I think it's kind of dangerous to not immediately recognize that there is such a thing as a one-sided and a two-sided limit. So as we see here, the limit as x, now this arrow, we're just getting introduced to limits, so it's important we know the notation. This arrow represents or is read as approaching. So we're not exactly at 0. X is approaching 0, just getting closer and closer and closer towards the x value of 0, both. Now there's no minus or plus as a sort of top exponent here, and not an exponent in terms of a mathematical operation, but there's no plus or minus indicated in the upper right-hand corner of the 0. This is a two-sided limit. Now we're going to get into this a little bit later, more specifically with some nice notation. But when I have a limit expression like this, many times, we're going to do 3 examples. We're going to step up the difficulty as we go. I'm looking at a parabola. I can see that it's smooth, and I was able to draw it. Smooth's not super important, but I was able to draw it without picking up my piece of chalk. So yes, when you're given a limit statement and it's not maybe a transcendental, or especially if it's not a piecewise function, if you could plug that number in, just plug it in. We have what's going to appear to be the same thing, 0 squared minus 4 times 0 plus 3 is once again equal to 3. So for our first example, evaluating a function at some value of x and evaluating a limit at some value of x appears to be exactly the same, but it's not. This statement, a function's value, is what y value are you getting from your equation when you're exactly right on that value of x, where x is equal to 0. A limit statement, do you have any red chalk? I know I do. A limit statement, and with there being no plus or minus, is about you approaching. What ultimately is the answer, the y value that you're getting from this function as you get closer and closer to the given value of x at which you're trying to analyze the limit from both the left and the right hand side. And this parabola is made up of an infinite number of points, and every single point has basically its own xy address. So every single point that I put on this parabola has potentially a different value of x, a different value of y. And if you're approaching the same y value from both sides, see, if I come in here and I come in here towards the left of 0, as I get closer and closer to 0, I get closer and closer to the y value of 3 from the left. And as I get closer and closer to 0 from the right, my y values maybe are really big at some point, even maybe possibly negative at some point, but I don't really care what's happening with in terms of limit statements. I don't really care what's happening to the vertical movement that far away from that particular value of x that I'm interested in. 2 units away is too far. As I come in closer and closer and closer, my values of y are approaching that same y value of 3. So indeed, a value from a function and a value that we get from a limit statement are sometimes the same, and they're often the same, but that's kind of boring. Anytime a function is continuous, anywhere a function is continuous, the value of that you get from the function, the y value, and the y value that you get from a limit statement are going to be the same based on the definition of continuity, where the function exists, the limit exists, the two-sided limit exists, and they're both equal. Now let's take a look at a slightly more complicated situation, which is example number 2. So what we have here is I would like to figure out what is f of 1. Okay. If we look at that, we're going to have negative positive 1 squared plus 1 minus 2 over 1 squared minus 4 times 1 plus 3. Okay, so we're trying to find the value of this function at the x value of 1. Well, we have 1 squared is 1, plus 1 is 2, minus 2 is equal to 0. And in the denominator, we have 1 squared is 1, minus 4 times 1 is 4, minus 3, so minus 4 plus 3. Well, we end up with 0 over 0. And how I'm showing my work here is fine for scratch work, but when you're taking an AP calculus test and how stringent that potentially the scoring of these answers you give can be, or maybe your classroom teacher, I said that f of 1 is equal to this expression. Yes, the original function with 1 plugged in, but then I wrote equals. Like every single step of my work, I have linked together with an equal sign, and that's very dangerous, actually. It means that you're saying that every single thing that you're writing is equal to the previous thing you wrote. And if you write something that is seemingly correct, in this case, yeah, my arithmetic is correct. When I plug 1 into the numerator and denominator, I get an answer that is 0 over 0. Well, this is not a real solution. And indeed, there may be, at least in terms of limits, a possibility of you finding an answer. In this case, and it's called in terms of limits in indeterminate form. But in terms of value that you get from a function, we're never allowed to divide by 0. So even though it's 0 over 0, and in a minute here I'm going to talk about how that's a little bit of a special case, this function f of x does not exist at the x value of 1. It's not part of the domain. We're going to talk about restrictions of domain. So f of 1, let's write it over here so I can leave it up, does not exist. This function does not exist at x equals 1. So the function value is undefined, if you will. Now, when we go to evaluate a limit, and it's that idea of approaching, the limit as x approaches 1 of x squared plus x minus 2 over x squared minus 4x plus 3. Now, I'm not going to take the time to write in the fact that I'm trying to plug in a value of 1, but this is going to be in the form of 0 over 0. That is indeterminate, which I can't remember if there's an E at the end of that or not, to be honest. When you go to find not a value of a function, but the value that you get from a limit statement, what is the limit for this equation, for this expression, or for this equation, what kind of answer you get when x is not exactly at 1, but approaching with the arrow, the word approaching 1. 0 over 0 is a special case, and there's actually lots and lots of forms of indeterminate. We're going to be learning that later in our calculus course, but this is one form of indeterminate. Now what that means is you still cannot divide by 0. You cannot divide by 0. The answer is undefined. But if it's 0 over 0 or some other special cases, in terms of limits, what that means is there may be one. There may be a solution or an actual finite answer, a real value that you can apply to this expression, even though the original function, the actual function itself, is undefined. So now we're getting into the nitty-gritty about what is the difference between the value of a function and the limit of that function at some point. We're going to look at the picture in a second, but right now we're going to talk about almost doing this in reverse. We're going to evaluate this limit analytically, not with a picture, but analytically. We're going to do that by factoring, trying to simplify this fraction to see if there's something that happens that's nice that allows us to, well, plug 1 in and get an answer. We're going to factor the numerator. What factors of negative 2, we have a leading coefficient of 1. So what factors of negative 2 add the 1? Positive 2 and negative 1. So we have the limit of x plus 2 times x minus 1. And in our denominator with the leading coefficient of 1, what factors of 3 add to negative 4? Well, negative 1 and negative 3. Now when we do that, we can see that we have factors of x minus 1 that are going to cancel, and we have the limit as x approaches 1 of x plus 2 over x minus 3. I don't know why I'm including all these parentheses. But see, this is an expression that we can plug in the value of 1 and get a real answer. Now here we're going to move sideways, and I'm going to go ahead and write equals because we're about to actually get an answer. Notice that there is a difference, that's what the whole point of this lesson is, between a function's value and a limit of a function approaching some value. So I'm using that limit notation through each line of work until now I'm ready to take this value of 1 and plug it in. The limit statement says limit as x approaches 1. But honestly, if you're able to take that value and plug it into the expression, you're probably pretty safe that what you're getting as an answer is good. So we're going to have 1 plus 2. Doing a little bit of scratch work here, so I'm going to go ahead and just start writing out without the limit statement. 1 over 1 minus 3. We have 3 over negative 2, so negative 3 halves. Why are we able to say that we have a limit, this function is undefined, at x equals 1, and by the way, now that we have this function in factored format, yes, we did a little canceling, but our denominator is made up of 2 factors, one of which is going to be equal to 0 when x equals 3, and one of which is equal to 0 when x is equal to 1. Well, you can't divide by 0, whether it's in terms of limits, indeterminate form or not. So our domain for this original function, something that's always a good idea to think of as you start any problem, is that x cannot equal 3 and x cannot equal 1. And the fact that there's a restriction on the domain, which is why I picked it for our problem, to have something interesting to talk about. Okay, so I want to focus on my original equation here, but I also want to graph this reduced form. I want to graph y is equal to x plus 2 So you can have now a visual representation of how to analyze limits over x minus 3. This is a nice clean way of analyzing this limit, which initially was in a form of indeterminate 0 over 0. But sometimes we have things like maybe if it were sine of x over x. Some functions we can't simplify into a format that allows us to plug in a value of c, or whatever your book is calling this constant, and get a limit. So sometimes you really do have to require on t-tables and graphs to come up with the answer to a limit statement. Now this is a polynomial over polynomial, so it's relatively, in terms of calculus, kind of simple. And if you remember graphing rational functions from pre-calculus, you might know that if you have a factor in the denominator that does not cancel, it is a location of a whole. So this rational function, and I'll have a link to a video about graphing rational functions if you need to review, this function will have a vertical asymptote at x equals 3. Because it's a rational function and we have a factor of x minus 3 in the denominator that does not cancel out. You also, in pre-calculus or algebra 2, when graphing rational functions, talked about locating horizontal asymptotes. And if the degree of the numerator and the degree of the denominator are equal, then the equation of the horizontal asymptote is made up of y equals, and you just work with the leading coefficients of both the numerator polynomial and the denominator's polynomial. So we have a horizontal asymptote of, with a degree of 1 in the numerator and a degree of 1 in the denominator, a leading coefficient of 1 in the numerator and 1 in the denominator. We have a horizontal asymptote of y is equal to 1. If the degree of the numerator when graphing rational functions is larger, there is no horizontal asymptote. If the degree of the denominator is larger, well, then the equation of the horizontal asymptote is y equals 0. In Chapter 2 of Calculus, we're going to be learning about evaluating limits at infinity, and we'll look a little bit more detailed about how you actually analyze that. Okay, let's see, what else do we have going on here? If we want a picture of this graph, just a rough sketch, I don't have anything but asymptotes. So I need something key to work on, like maybe like an, like maybe an x and y intercept. If I find, I'm going to find a y-intercept by letting x equal 0. I'm going to need to erase this in a minute, but we're going to find a y-intercept by letting x equal 0. Well, we kind of already did that. When we let x be 0, we're going to have an answer of, actually, no, we didn't, of 2/3. So great, negative 2/3. Okay, let's go ahead and find a x-intercept. Now, if you find a y-intercept by letting x be 0, you find an x-intercept by letting y equal 0. Well, the only way you're going to figure this out, where 0 is equal to x plus 2 over x minus 3, the only way a fraction is going to be equal to 0 is if the numerator is equal to 0. And the numerator, which is x plus 2, is going to be equal to 0 when x is negative 2. So we have a y-intercept of negative 2/3 and an x-intercept of negative 2. And there's no other intercepts along the x and y axis. And I don't want to spend even any more time sketching this function. It is just a sketch. But we're going to approach those horizontal and vertical asymptotes, and the graph is going to look something like this. Now, I know this very simple rational function is not going to cross a horizontal asymptote. It is possible for a function to cross a horizontal asymptote, but it will approach it over the long run as it approaches infinity or negative infinity. So this is basically what our sketch is going to look like. Now, this is a sketch of the function y is equal to x squared, y is equal to x plus 2 over x minus 3. We used this function to analyze this limit where x is approaching 1 of x squared plus x minus 2 over x squared minus 4x plus 3. When we got an answer of negative 3/2. But this is not a graph of the original function. This is a graph of our reduced function. There is a difference. it comes from the fact that we had a factor of x minus 1 cancel out. This blue function is said to agree, because it was basically derived from the original function. This function agrees with our given original equation everywhere except, well, x equals 1, because this function was undefined there, which means that this function, if you go back to your pre-calculus in Algebra 2 when you graphed rational functions, when you had factors that were able to cancel, those were locations of holes. So while this blue is a graph of this function, our original function actually had a hole at -1. I'm trying to maybe change the color, but I'm just not going to. We'll do it in red. So we're going to be coming through here, and when x is equal to +1, where this function was undefined, there is a location of a hole. And then we pick right back up with the rest of the graph from y is equal to x plus 2 over x minus 3. And here in red, if you can see that on the camera, is the graphical representation of our original function. Now, if we had this graph given to us either instead of or in addition to our original problem, and we were asked to analyze the statement, find the limit as x approaches 1 of this function, this fraction, and recognizing that there is no plus for a right-hand limit and no minus for a left-hand limit, and we see that this is a two-sided limit statement, this has an answer as long as you are approaching the same y value. And my picture's a little bit off because it's really supposed to be negative 1.5, but as long as you approach the same y value from the left and the same y value from the right, then that two-sided limit exists, and you could look at the picture and see that the answer is negative 1.5. So yes, there is a difference between a function's value at a point and the limit of a function as that function approaches that same x value. I think I might have said the y value over there. If at a point either the function does not exist or the two-sided limit does not equal the function's value, then you have a discontinuity at that point. And yes, this function was discontinuous at x equals 1. That's why this, hopefully, you found to be a nice example. Let's get on to example number 3 and having a little bit of interest in it. Great. Okay, so for our third and last example, we have a piecewise function. And we have f of x is equal to negative 1/4 x plus 4. We're going to be using this first function when x is less than 3, or to the left of 3. When x is exactly 3, our piecewise function is going to give out an answer of 1. And when x is greater than 3, we have x minus 3 squared. Piecewise functions are what the US government, and probably many governments, use to calculate your income tax. The more money you make, at least in the US, the higher the percentage of your income goes to income tax. And so they divvy it up based on brackets of income, piecewise functions. So they have a real-life application. Well, as we look at this, and I alluded earlier, and it's, well, I stated that if a function is continuous, then the function value and the value of the limit statement at that same value of x are going to be equal. The interesting stuff happens when a function is potentially has a discontinuity. So the fact that we have a line, negative 1/4 x plus 4, a linear polynomial, or a polynomial with a degree of 1, that's a line that's continuous everywhere. This is a parabola that's continuous everywhere. So the fact that you see a piecewise function broken at the x value of 3 means, well, that's the opportunity of us to have some discontinuity here with this problem. And I do want to find a two-sided limit. I do want to find and look at the value of the function at 3 and the limit of that function as x approaches 3. And again, analyze the differences between those two statements of a function and limit value. We're going to do this with a picture first, because it's important we know how to graph piecewise functions. Our first function, which we'll do here in blue, is a line whose y-intercept is 4 and whose slope is -1/4. So we're going to go up to 4, and then we're going to go down 1 and over 4. 1, 2, if I can count, 1, 2, 3, 4. So this is the graph, kind of, sort of straight, of y is equal to -1/4 x plus 4. But I don't want the entirety of this line. I only want to, the piecewise function is only using the equation of that line when x is less than 3. So I don't want anything to go past the x value of 3, and there's no equal sign, so it's going to be an open dot. Now, when x is exactly 3, and only at exactly 3, we have a y value of 1. So we're going to come in here at x equals 3 and put a solid dot at y equals 1. Now, when x is greater than 3, I want to have us look at something squared, x to the first squared. So this is a parabola. That parabola, we have a leading coefficient of just +1, so that parabola is opening up. And hopefully you remember your parent function, y equals x squared is just simply a parabola opening up, going through the vertex. And this -3 that's inside that math function of power of 2 is going to shift the graph to the right three spaces. So we're going to go over here to 3, 0, put a dot. We don't have any vertical stretch applied to this parabola, so we're going to go over 1 and up 1. And kind of just continue to sketch it. We're going to have an open dot down here and have a parabola opening up. Now, now that we have a picture or we have an equation to work with, I want to analyze what f of 3 is. Oh, well, we said that. If x is equal to 3, the y value is 1. Great. Is the limit as x approaches 3 of f of x, what is that equal to? Well, often when analyzing limit statements, whatever that value of c is, you can just simply plug it into the function. But that's not so good here because, well, we can see for two things. Our function is clearly broken. There's a discontinuity. I have to pick up my pencil to draw the picture, if you will, and you got to be really careful with that. Now, another thing is we're approaching. It's the limit as x approaches with that arrow 3, not exactly at 3. And this is with no indication of plus or minus in the upper right-hand corner of our 3. This is a two-sided limit. And we have something going on. Now, a two-sided limit will only exist if the limit as x approaches 3 from the left is equal to the limit as x approaches 3 from the right of f of x. Now, did you see what I did there? When I said the word left, I put a negative, and when I said the word right, I put a positive. And looking at the picture, what y value, f of x is like a fancy function notation of writing y, what y value am I getting from this graph or within this graph or from this function when x is approaching 3 from the left? Well, I'm up here at a y value maybe of who knows, 10, 7, 6, 5, 4, but as I get really, really close to 3 from the left-hand side, I'm going down and getting closer and closer and closer and closer to, and I guess I didn't draw this very well because that should, oh, I guess so. Well, I don't really know what that is. I can't eyeball what that number is. That's what happens when you make your own answer up. But it's some relatively large number, and you know what you can do? What you can do to analyze this statement if the picture is unreliable is we're going to take the value of 3, and we're going to literally not plug in like something a little bit less than 3, like 2.99. You could, but you don't really need to. We're going to plug the value of 3 and indicate that we're looking just to the left of 3 by using the expression that says use this when you're just to the left or a lot to the left of 3. So we're going to do negative 1/4 times 3 plus 4, which is going to be negative 3/4 plus 16 over 4, and that's going to be 13 over 4. That's what happens when you make your own examples sometimes. And on the right-hand side of 3, the limit as x approaches 3 from the right, well, if you're approaching 3 from the right, you're using x values that are larger than 3, not x values that are smaller than 3. So you can do one of two things. You can take the value of 3 and plug it into the expression that you're using when x is larger than 3, or if you can eyeball it reliably with the graph, do that as well. As we approach 3 from the right and visualize what's going on with our picture, we're getting closer and closer and closer, not exactly at, but approaching a y value of 0. Now the left-hand limit does not equal the right-hand limit, which means that the answer to the limit as x approaches 3 of f of x, well, it turns out it doesn't exist. The answer is, basically, it does not exist. So we saw an example where the value from a limit statement and function statement were equal. That's going to happen when a function exists and a two-sided limit exists and they're equal. We have continuity at a point. We had an example where the function did not exist, but the limit did. That's going to occur when the graph has a hole in it. You can see that. And we have here where a function did exist, but the limit didn't exist. And it's possible that a function exists and a limit exists, but they're not equal. So you have a discontinuity there as well. So I hope this helps you understand the differences between function values and limit values. I'm Mr. Drew. Bam! Go to your homework.